Assalamu alaikum everyone. I hope you guys are doing well. We're going to go over the notes first and then do past papers, okay? I'm so sorry. I've been trying to record lessons, but there's been so much going on with my own academics that I couldn't get a chance to, but I have my reading week. Yay. So we're going to get some lessons done. The first one we're focusing on today is kinematics or motion. As I said, we're going to go over these pre-written notes. I won't be able to go in a lot of detail, but I should cover sufficient amount of information for you to get an A star. If you guys don't get an A star, I'm coming with a knife in my hand. I'm gonna hunt you guys down and make sure that I get my time back. Just kidding. You'll be okay. And yes, before I start, I definitely have a humor of a second grader, so please ignore it. Okay, so the first thing is a physical quantity. A physical quantity is anything that you can measure, whether it's the length of a table, the height of a person, anything that you can measure, anything that's tangible is a physical quantity. There's two characteristics. You have the magnitude and the SI unit. The magnitude tells you the size of the quantity, it's a number, okay? And the SI unit tells you the type of quantity. It gives you more context into what we're talking about. So we have two numbers, 60 and 70. We know that 70 is bigger than 60, so it gives you an idea about the size of the quantity, okay? You would know one is more than the other. And the unit, like kilograms and newtons, gives you context into the type of quantity we're talking about. When you hear 60 kilograms, you know we're talking about mass. When you hear 60 newtons, you know we're talking about a force, right? Now, we have two types of physical quantities. We have scalars and we have vectors. A scalar and vector. Oh, so these two quantities are different um, in one aspect, such that a vector has an additional property called the direction. Not called, but the property is the direction. Let's take an example. If I say that a car is moving at 40 kilometers per hour, that 40 kilometers per hour has the magnitude and the unit. So that's a scalar. But if I add a direction in it, if I say it's moving due north, that becomes a vector. So when you couple a direction with a scalar quantity, it becomes a vector. Okay? Now we're going to talk about some main types of scalars and vectors. I've color coded them. Scalars are on the left side, vectors on the right side in pink. Let's go over them one by one. So distance. Let's understand distance and displacement. Imagine you have a start position and end position. Okay, so you go from your house to the school and you take the blue road or blue path. Now, the actual path that you cover is the distance. And most of the times you don't have a straight road from one point to another because of certain obstacles or, I don't know, constructional reasons or whatever. Um, this total length that you cover to go from your start point to the end point is your distance. So what's distance? It's the total length covered by a moving object regardless of the direction. And why do we not take direction into account? Because you would notice it's a curved path. It's not a straight line. And remember that for curved paths, we determine direction by drawing tangent lines. What's a tangent line? We take a single point and you draw a straight line at that point. That's a tangent line. And the tangent line gives you direction at that very instant, at that very point. Okay? And you would notice that if you drew 2 to 3 tangents, like this one here, and let's try another one here, all of these arrows point in different directions. So that means the direction is changing at every instant. You do not have one single direction. That is why we say distance is scalar because it doesn't have a single direction. And displacement, let's talk about that now. If you were to extend a straight line from the start point to the end point, you will get displacement. It's the shortest length from your start point to the end point in a straight line, and since it's in a straight line, you can give it a single direction, and in this case, it's northeast. Okay? Now, since both of them are lengths, they have the unit meter. Okay? Now, if you divided distance by time, you would get speed, and if you divide displacement by time, you'll get velocity. So speed is distance divided by time. If you want to put it into words, it's rate of change of distance, and velocity is displacement divided by time, rate of change of displacement. Okay, now units. So speed is distance over time. Distance has a unit of meter, time is seconds, so meters divided by seconds is meters per second. Likewise, displacement is meters, time is seconds, so meters per second. So both of them have units, meters per second, meters per second. I'm not going to go over this example, but you can pause the video and look at it if you want. It's just a simple calculation. And then we have another example. Again, I'm not going to go over it. I'll probably record some detailed lectures to go over these things. For now, we're going to skim through the important points. Now, another important thing here is that distance is always greater than or equal to displacement. You saw in the diagram above that this was your start point, this was your end point. The curvy path, or the curved path, was your distance, and the straight line was your displacement. Now, if you have a curved path, your distance is greater than the displacement, right? So distance is always greater than displacement unless you have a straight line road or straight road, okay? In that case, your distance would be equal to displacement. So if, let's say you have a straight line or a straight road, your distance, if the car goes from the start point to the end point, the actual path that the car follows is a straight line, so that's your distance. And the displacement is also a straight line from the start point to the end point. So in this case, your distance is equal to the displacement. Okay? So you have this important rule that distance is always going to be greater than or equal to displacement. I hate R's. I can't say R's. I'm sorry. Okay. You know what? I can't say words that have R's, like greater, uh, water. Ugh. Anyways, sorry. Uh, okay. Wait. I have another email. What is up with the emails? Please don't send me emails. I hate emails. Sorry, I'm gonna take a little second to read it because I'm distracted otherwise. Where did you go? Do you guys give me one little minute to type a response? Okay. Okay, we're done. A summary of what we've done so far: scalars and vectors, two types of physical quantities. Vectors have direction. Distance is the total length from start to end point. Displacement is the shortest length in a straight line. Divide distance by time, you get speed. When you divide displacement by time, you get velocity. The next thing we have is acceleration. Now, if you divide the change in change in velocity by time taken, you get acceleration. Okay. Do I want to go through the details? Yes. Do I have time for that? No. I think I'll skip over it for now. Let's go through the units. So acceleration is change in velocity over time taken. Velocity has a unit of meters per seconds, and time is a unit of seconds. So if you write it like this, meters per second divided by seconds, and then you reciprocate this, so meters per second comes as it is. You change the division sign into multiplication, and then you have to take the reciprocal of the preceding term, the following term. You will get 1 by second. So m multiplied by 1 is m. Seconds multiplied by seconds is seconds squared. You don't need to go through the derivation. Just learn that the unit of acceleration is meters per second squared. Okay. Acceleration, you have two types of acceleration. You have uniform and non-uniform acceleration. Just think about school. Uniform is same for everyone. So uniform acceleration is same for every interval. Okay? And non-uniform acceleration is variable for every interval. Let's take an example. You have a car that is going or moving on a straight road, okay? And you record its velocity at every 1 second interval, okay? So after every 1 second, you take a snapshot and you look at its velocity. After 1 second, the velocity is 1. After another second, the velocity is 2. And after another second, the velocity of the car is 3. Okay, so after every 2 seconds, sorry, oh, what am I saying? Okay, okay. Guys, I have no energy to edit this video and cut out my glitches. So please ignore my sorries and I don't know, it's 10 p.m. for me and I'm trying my best not to quit. And this time I'm not gonna quit, okay? Calm down. You can do this. Yeah, so we're gonna record the journey after every 2 seconds. So at t equals 0, the car has a velocity of 0. At t equals 2, the car has a velocity of 1. At t equals 4, the car has a velocity of 2. At t equals 6, the car has a velocity of 3. So we're recording the velocity after every 2 seconds. So one interval is 2 seconds. Okay? So now you see that after every 2 seconds, the velocity increases by 1 meters per second. So what you're going to do is find the acceleration in every interval. Acceleration is change in velocity over time taken. Your change in velocity is 1 and the time taken in this interval is 2. So your acceleration for this interval is a half. Your change in velocity in the second interval is 1 and your time taken is 2. Again, acceleration is 1 over 2. Change in velocity is 1, time taken is 2, acceleration is 1 over 2. So you see the acceleration is constant in every interval. So that is uniform acceleration. On the other hand, your change in velocity is variable. Okay, in the first 2 seconds, it increases by 5 seconds. In the next 2 seconds, it increases by 3 seconds. And in the next 2 seconds, it slows down by 2 meters per second. So you will find the acceleration in every interval, 5 by 2, 3 by 2, and -2 by 2. So you will notice that the acceleration of all of these intervals is different. So it's changing, it's variable. That's called non-uniform acceleration. We have a question. You might want to pause and look at it if you want. I will skip over it for now. So we're done with the first section of kinematics. Let's move on to the next section, which is graphs of motion. These are very, very interesting. I love these because they're the same. I think I might not want to go through the details. I would go to the summary here. It's really cutesy. Okay, so we have two types of graphs. We have distance time graphs and we have velocity time graphs. The basic graphs are going to be the same. Okay? What is that? The plan. Okay, ignore that. So we have distance time graphs. The first thing you guys need to know is that the gradient of these graphs depicts important information. The gradient of a distance time graph tells you speed, and the gradient of a velocity time graph tells you acceleration. Again, we're skipping the details for now. When I record detailed lectures, or I might have done that, I'm not sure if I did. There I explained where this is coming from, but for now just remember that the gradient of a distance time graph tells you speed, and the gradient of a velocity time graph gives you acceleration. Now guys, you have to say it out loud with me. We have four types of graphs. We have a horizontal line, a straight slant line, an upward facing curve, and a downward facing curve. Our drill starts now. The gradient of a horizontal line is 0. The gradient of a slant straight line is constant. The gradient of an upward facing curve is increasing, and the gradient of a downward facing curve is decreasing. 0, constant, increasing, decreasing. We're going to say it 3 times, okay? 0, constant, increasing, decreasing. And when you say it, look at the shapes of the graphs and make sure it's marinating in your brain. 0, constant, increasing, decreasing. Okay, one last time. Horizontal line, 0. Straight slant line, constant. Upward facing curve, increasing. Downward facing curve, decreasing. Okay? So the gradient of a distance time graph tells you speed. Let's do that again, but use the term speed instead of gradient. The speed in this graph is 0. The speed in this graph is constant. The speed in this graph is increasing. And the speed in this graph is decreasing. Wonderful. Let's do the same thing for velocity time graphs. This time the gradient gives you acceleration. Oh, thank God it's recording. For a moment, I thought it's not recording, and I was gonna throw my iPad to the other side of the room if that had happened. I already have cracked screen. Anyways, my poor iPad, it's been with me for a few years. I wouldn't do that to you. I'm sorry, my little iPad. Okay, so a velocity time graph, what was I saying? Oh, yeah. So the velocity time graph, the gradient gives you acceleration. Acceleration of a horizontal line, 0. Acceleration here, constant, increasing, decreasing. So let's do that again using the word acceleration instead of gradient. In this velocity time graph, acceleration is 0. In this velocity time graph, it's constant. Here it's increasing, here it's decreasing. In the detailed lectures, again, I've gone through a lot of detail about why it's increasing and decreasing. But again, I'm so sorry we don't have time for that. So I will just make you guys cram at the last minute. Okay, so those are the two important things. In your exam, you'll probably get a combination of these graphs. For example, look at this one. It has a slant line, it has a horizontal line, and another downward facing, like negative slant line. So they're just going to combine these things, but the basics will be the same. So when you see a horrible when you see a horrible graph, just make sure you go back to the basics and see how you can dissect your graph into the basic graphs that I've taught you guys, okay? Now, another important thing is the uh, area under the velocity time graph. For the velocity time graph, you will be asked to find the distance traveled by the car or the moving object. So the area under the velocity time graph gives you distance, okay? Look at this horizontal line. If you have a horizontal line, you will just extend a line down and form a rectangle, okay? And then you'll find the area of this rectangle. The formula for area of rectangle is length into width, so you need to learn this formula. And you will just find like you'll just plug in the length and width of this into this formula and you'll find the area under the graph, and that will be the distance covered by the moving object. Next, you have this graph, which is a slant line. You'll do the same thing. You'll extend a dotted line down and form another shape here, which is a right-angled triangle. And the formula of the area of a right-angled triangle is 1/2 base into height. This is the base, and this is the height, okay? So you'll plug in numbers, you'll read the scale and plug in numbers, and we're going to do a lot of examples for this, so don't worry. And lastly, you have this shape, which is a trapezium. And how do you identify a trapezium? You have two parallel lines, okay? They can be of any length, and then these parallel lines are joined by two other lines. A trapezium can be anything. It can be like this, it can be like this. It just has to have two parallel lines and two connecting lines, okay? And what's the formula for area of a trapezium? Here I've done a different method, but I think trapezium formula is more efficient. So you'll just, oops, so you'll just do area is equals to 1/2 a plus b into height. Now, what's a and what's b? A is your first parallel side, b is your second parallel side, and h is the distance between these parallel sides or height. Okay, so we're officially done with the uh, notes for this section. Let's move on to the past papers now. By the way, the different method that I was talking about is just that I dissected this graph into three portions. Like the first one's a right angled triangle, the second one's a rectangle, and the third one's, excuse me, also a right angled triangle. I was so another method is that you can just find the area of these three shapes and then add that in the end, but it's very inefficient, and a lot of times students make mistakes in that. So please learn this formula instead. Okay, let's do notes now. Not notes, sorry, past papers. Okay, actually, study B. I'm going to export some these lecture notes, like duplicate them, and bring this copy in this folder. Okay, we're gonna do these past papers. Yay, I did my study session. Let's start another one. Guys, I studied for 5 hours today. I've been behaving myself. Should I count this as a study session? I don't think so. Or maybe I can. I'm working, right? Okay. Question number 1. The graph shows how the speed of a car varies with time. Which statement about the acceleration of the car between 10 seconds and 20 seconds is correct? Let's do it together. You guys know this, okay? You know this. The first thing is to pay attention to the question. Half of your answer is in the question itself. Remember that, okay? It's asking you the acceleration between 10 and 20 seconds. So first of all, extend your line up and look at what you're asked. There you go. So they're asking you about this portion. What does it look like? A horizontal line, right? And you guys know that the gradient of a speed time graph or a VT graph, for a VT graph, gradient is equal to acceleration. And what did we learn? A horizontal line has a gradient of 0, so acceleration here is 0. The acceleration is 0. Yay, we knew this. Remember, guys, I'm sorry if I haunt you in your dreams about this, but you need to learn this. For any graph, horizontal line, gradient is 0. Slant line, gradient is a constant number. It can be any number which is constant. Upward facing curve, gradient is increasing. Downward facing curve, gradient is decreasing. Okay, question number 2. A student walks at a constant speed. He takes 100 seconds to walk 160 paces. The length of each pace is 0.8 meters. How far does the student walk in 50 seconds? Pause the video, try to attempt it yourself, and then look at the solution, okay? There's no point of looking at the solution right away. Or if you think that you want to warm up a little bit, then maybe look at the solution for the first 5, 6 questions, and then pause the video and go ahead with watching the solution after you've attempted it once, okay? Now, okay, so what they're asking us is how far does the student walk in 50 seconds? So that is definitely the distance, right? How far someone's going means they're asking you the distance. So we want to find the distance, okay? The speed is constant and he takes 100 seconds to walk 160 paces. And they're asking how far does the student walk in 50 seconds. So if the student is taking 100 seconds to cover 160 paces, that means in 50 seconds, the student will take half of those, right? Will walk half of those paces. So that is 80 paces. The length of each pace is 0.8. So if 50 paces are in 50 seconds, the student walks 50 paces, and each pace is 0.8 seconds. Sorry, meters. So 80 paces will be 80 multiplied by 0.8, 0 is going to be. I'll be right back. I gotta run and get my calculator real quick. And also, I need to fill my water bottle. I'll take no more than 60 seconds. Count. Was that more than 60 seconds? I think so. I'm sorry. It was a lot of stuff. My water bottle is too big. And then I went into the room. Okay. No, no, no. Sorry. Let me stop there. Basically, I had a little fun teasing session with my sister. I was teasing her because she was on her phone, and I was telling her not to be on her phone and go to sleep. Yeah, and I stashed her phone and came out of the room. Being an elder sibling comes with a lot of responsibility. If you're an elder sibling, you know that. And the benefit is that you get to bully them without any accountability. See, sorry. Okay, stop, stop, stop. My Apple Pencil's gonna die. No. Okay, let's wait for 1 minute. Ah, what? I went to get the calculator for this calculation? Bro, sorry. So 80 Okay. Reset button. Okay. We're back to the teacher mode. Okay. So 80 multiplied by 0.8 is just 64 meters. So our distance is 64 meters. There we go. Okay. Next, a student drops from rest a table tennis ball in air. What happens to the velocity and to the acceleration of the ball during the first few seconds after the release? Okay, so you have a tennis ball and you drop it, okay? You drop it. That means initially it had no velocity. If you're throwing something, it has an initial velocity. But if you're dropping something in the air, its initial velocity is zero. So its initial velocity u is zero. When you drop something, the acceleration, it's going to accelerate because gravity is attracting it towards the ground, okay? So its velocity is going to increase. It will speed up. So its velocity increases. And first few seconds. Okay. First few seconds after release. Yeah. Its velocity increases, and if its velocity is increasing, its acceleration will also increase. I feel like it's D because it's saying in the first few seconds after release. However, if it was, yeah, in the first few seconds, its velocity is going to increase and it's also going to accelerate. However, in the later seconds, like in the later part of its journey, what will happen is that let's draw a few snapshots of the ball's journey. So in the first few seconds, you drop the ball, its velocity increases and it accelerates. And then let's say after a few seconds, it's here. Now, as its velocity increases, its air resistance is also going. The resistance that it faces due to air is also going to increase. That's just a law that friction or air resistance is proportional to the speed of the object. Imagine that you're walking on the road, okay, and you don't really feel a huge force of air on your face, but as soon as you start running, you feel more air uh, against your face, right? And if you start running faster and faster, you will feel more and more force of air, right? So the rule or the law is that as an object speeds up, the resistance that it faces also increases. Because resistance or air resistance or friction is an opposing force. It tries to stop moving objects. So the faster something's moving, the more the resistance will be in order to stop the motion of that object. Okay? Okay, so here as the object's velocity has increased, its air resistance will also increase. And then after a while, oops, let's say the ball's here. Now this is the velocity, then the air resistance will also increase and the object will be in equilibrium. So basically, object will be in equilibrium. And as your opposing force increases, the object starts to decelerate. Not decelerate. Yeah, it does decelerate. We'll cover this concept once again when we see a question about terminal velocity. So for now, maybe I should get rid of it as to not confuse you guys. But in the first few seconds, it definitely, the velocity increases and the object accelerates. Question number 4. A cyclist takes a ride lasting 25 seconds. The diagram shows how her distance traveled from the starting position varies with time. What's her average speed for the whole ride? How do we find average speed? The formula for average speed, we saw that in the notes, is total distance over total time taken. Time taken. So the ride ends at 25 seconds. So what's her distance at the end? 150. And how much time did she take for that? 25 seconds. So that would be 6 meters per second. There we go. A car begins to move. It speeds up until it reaches a constant speed. It continues to travel at this constant speed for the rest of the journey. What happens to the acceleration and what happens to the velocity of the car during the journey? So you have a car, it begins to move. So its initial velocity was 0 and then it begins to move. And then it speeds up. So here you have some velocity v1, okay? It's sped up and then it reaches a constant velocity and let's call that v constant, okay? So it continues to travel at the constant speed. You have two intervals, and then okay, so after this it continues to travel at the same speed. So you have two intervals. You have your first interval where the car is speeding up, okay? When something speeds up, we say that it's accelerating. And then you have your second interval where it reaches a constant velocity. Basically, your second interval is also speeding up where the car reaches a constant velocity. So basically, I can call this one interval where the car is speeding up from 0 to a constant velocity. In your second interval, it just continues with the same velocity. Now, in your first interval, the velocity is increasing. The car is speeding up, so it's accelerating, okay? When something is speeding up, we say that it's accelerating. And then the car travels at a constant velocity. Recall the definition of acceleration. Acceleration is change in velocity over time taken. If something is speeding up, there is a change in velocity. The change in velocity is increase in velocity, right? Change is increase or decrease. So when we have a change, we know that the object is accelerating. But when it's traveling at a constant velocity, there is no change in velocity. So the change is 0 divided by whatever time it takes for that. So 0 divided by any number is always 0. So the acceleration here is 0. Okay? So remember, when something's traveling at a constant speed, its acceleration is 0 because it's not changing its velocity. Okay? So both the acceleration and velocity change. Only the acceleration changes, only the velocity changes. Neither the acceleration nor the velocity changes. Both the acceleration and velocity change. There we go. I'm just trying to go over the options once again to make sure. Yeah, I think A is okay because they don't mention anything about the rate of change of the speed. It just says it speeds up, right? So the acceleration can be uniform or non-uniform. So I think the safe option would be A. Let's move on to question 6. An object travels at a constant speed of 10 meters per second for 10 seconds. So it's this part of the journey. During the next 5 seconds, it accelerates uniformly. Now it does mention uniform acceleration to 20 meters per second. So here the uniform acceleration is shown and it goes up to 20 seconds. What's the total distance traveled by the object? Okay, so remember, how do we find the distance traveled in a speed time graph? We find the, yes, area under the graph. Area under the graph. Okay, now we can extend a line down here and we can extend a line down here. Okay, the first shape, what's the first shape? What do you guys think? If you don't know this, please go back to grade 1. Actually, kindergarten. We learned this in kindergarten. Anyways, okay. So this here is a rectangle, okay? Area of a rectangle is length into width, okay? Your length is 10 and the width is also 10. So I'm just going to call this shape 1 and call this one 2. So A1 is just length into width, and that is just 10 by 10, which is equal to 100 meters squared. Oh, sorry, meters. Because, yeah, it's meters because your units will cancel out. For length, the unit is seconds, and for speed, which is the width, the unit is meters per second. This second cancels out with this second, so you're left with just the meter. But that's not important though, you can skip it for now. Okay, so A1 is 100. Let me put this up here. This can go here, and this can go here. And I can color this green right there. Okay, now let's find A2. So this is your second shape. What did I say? Whenever you have two parallel lines, so this is your parallel line, and then this is your parallel line. And then you have two lines connecting those parallel lines, that's a trapezium, okay? So this shape here is your trapezium, trapezium, okay? You can call this A2. What's the formula of, what's my battery? 8%, not bad. 1 over 2, A plus B times height. What's A and what's B? A and B are your parallel sides. This is A, this is B. And the distance between those parallel sides is your H, okay? So 1 over 2, A is 10 plus B is 20 multiplied by the distance between them is 15 take away 10 is 5. Okay, don't, please don't take 15. I'm gonna cry if you do that, okay? So when you take this length, don't take the entire length, okay? 15 is the entire length. You want this length, which is 15 take away 10, 5. That would just be 1 over 2, 30 by 5. You can cancel these out. 15 by 5 is just probably 75. 75 meters. So A1 is 100, A2 is 75. In the end, you just add them. So area, total area is just A1 plus A2, which is 100 plus 75 equals 175 meters. Yay, we've done. this question as well. Okay, wonderful. Let's do question number 7. A lorry takes 15 minutes to travel along the path PQRS. So it takes 15 minutes. What's the average speed? Again, what's the formula for speed? Speed is equal to average speed is equals to total distance over total time taken. What's your total distance? Just add these numbers up. It travels 8 kilometers here, 3 kilometers, and then 5 kilometers. So that's just 8 plus 3 plus 5. Now, what's your time taken? 15 minutes. Look at the units of the question. Kilometers per hour. Kilometers per hour, kilometers per hour, kilometers per hour. That means you have to convert this into hours. So look at this conversion factor now. You have seconds to minutes to hours, or let's do it the other way around first. Oops. Okay, so if you're going from an hour to minutes to seconds, 1 hour has 60 seconds. So to go from hours to minutes, you multiply by 60. 1 minute has 60 seconds. So to go from minutes to seconds, you multiply by a 60. And to go directly from hours to seconds, you multiply by 60 twice. So that means you just multiply by 3,600. Now, to go from seconds to minutes, you know that 1 second won't even have 1 minute, right? 1 second will have a fraction of a minute. So you will divide by 60. To go from minutes to hours, you will divide by 60. And to go from seconds to hours, you'll do that twice. That just means you're going to divide by 3,600. Okay? So we're going from minutes to hours. So we're going to divide by 60. Okay? So 15 over 60 is just 0.25 hours. 0.25, and that is 8 plus 3 plus 5 over 0.25 is 64 kilometers per hour, part option D. Okay, let's move on to the next one. At time t1, a stone is dropped from a stationary balloon. Okay, the stone reaches terminal velocity at time t2. Which row gives the acceleration of the stone at time t1 and time t2? Now we need to look at the idea of terminal velocity. It's very important. Okay, let's do it here. Let's say you drop a stone, okay, at t equals 0. At t equals 0, when you drop the stone, its initial velocity is 0 because you're not pushing it, you're not applying an external force, so your initial velocity at this point is 0, okay? And the stone will, of course, fall down, right? When you're dropping it. The stone has a certain weight. Let's call it W. It has a downward force, weight, W, okay? Now, as the stone falls down, let's say it reaches this point here. Oops. Let's say, and imagine you're dropping it from a very, very tall building, okay? So let's say the stone reaches this point and you're looking at it after 2 seconds. After 2 seconds, of course, the stone has sped up a little bit. Its weight will be the same. Of course, it's not going to change because weight depends on the mass of the object and the gravitational field strength of the planet it's on. I'm going to take the same circle just to be consistent. There you go. Now, as the stone falls down, after 2 seconds, it will speed up. Its velocity will increase, right? So its velocity, let's say, is now 2 meters per second, okay? Now, as the velocity of the object increases, what did I say before? It will face more resistance. The air resistance will also increase. So you get a tiny bit of air resistance here, okay? We're going to do this again. After another 2 seconds now. So let's say at 4 seconds, the stone has 4 meters per second velocity. So as the velocity increases, what happens? The air resistance, which is an opposing force, a force that tries to stop motion, will also increase, okay? If the balls or the stones moving down, air resistance will be opposite to that, which is upwards. So I'm just going to call this little f here for air resistance. So the air resistance is increased to this much. Now, the stone's still falling. It's dropped from a tall, tall building, okay? I think I should use dotted lines to show that we have snapshots of the same journey. There we go. Now you see the upward arrow and the downward arrow are kind of equal. Let's look at the journey after another 2 seconds. After another 2 seconds, let's say at 66 seconds, the stone is now moving at 6 meters per second, okay? And its velocity, the upward force increases as well. The air resistance increases as well. At this point, your upward force is equal to the downward force. So your friction is equal to the weight. When the opposite forces are equal, remember this point, when opposite forces are equal, the net force, F net, is 0. Okay, net force is 0. Remember that for anti-parallel forces, or forces that are opposite to one another, we find the net force by subtracting one from another. So if the weight of the stone is, let's say, 20 newtons, if it's a heavy stone. So if the weight of the stone is 20 newtons, the air resistance now has also reached 20 newtons. When you take 20 away from 20, you get 0. So your net force is 0. The weight will always be 20 newtons because it depends on the mass of the object and the gravitational field strength. The formula of weight is this, W equals mg. So weight depends on the mass, and mass is the number of particles in an object. It doesn't change anywhere in the world or the universe. I'm not going to get into general relativity or other stupid things. Not stupid, actually cute things that you might learn at a higher level. But the mass of the object is constant. Gravitational field strength, the value of G depends on the planet. You're on the same planet, so your weight is going to be the same. But here, let's say the upward force is 5 newtons. Here it's 10, and now it's reached 20. When your opposite forces are equal, the net force is 0. Here your net force would have been, what do you guys think? 20 take away 10 is 10 newtons. Here your net force is 20 take away 15 newtons. And in the very start, when the object has just started moving, when its initial velocity is 0, there is no upward force. Your net force is just the downward force, which is the weight. So F net is equal to 20 newtons, okay? So you see how the net force has gone from 20 to 15 to 10 to 0. So your net force has eventually decreased to 0. Now, recall Newton's second law, F net equals ma. It says that the net force in an object is the product of its mass and acceleration. I said earlier that mass of an object is always constant, at least in your course. Constant. So if the net force is changing, that means this number must be changing because this is a constant. It's always going to be the same. This number is not changing. If the left-hand side is changing, the right-hand side must be changing. There must be something that's changing here. So that's definitely the acceleration. So if this is constant, we know from math that we can write it this way as well, that F naught is proportional to acceleration. Okay, you might have learned from math that when you have proportionality between two things, you can get rid of the proportionality sign by introducing an equal and a constant k. In this case, our constant is m. Okay, so your net force is directly proportional to acceleration. So if your net force, what does directly proportional mean? It means if one thing is increasing, the other will increase as well. And if one thing is decreasing, the other will, yes, it will decrease. So if your net force is decreasing, what's happening to the acceleration? It's decreasing. So here, your acceleration will decrease. Acceleration. And eventually, what happens to the acceleration? It becomes zero. Because F net, when will F net be zero? When M will be multiplied by zero. You only get zero when when in a product one of the numbers is zero, right? At least one of the numbers. Mass is not zero, then acceleration must have been zero. And when your object reaches constant velocity, that is called terminal velocity, basically. So your constant velocity is called terminal velocity. So terminal velocity is just a fancy name for constant velocity. Okay, let's do a quick recap. The things that you need to remember are that as an object speeds up, the opposing force or air resistance, which is a form of friction, increases. And as the opposing force increases, the net force on an object decreases. And when the net force is zero, the object has reached terminal velocity. Okay? And at that point, acceleration of the object is equal to zero. Okay, so the stone reaches terminal velocity at t2. Acceleration of the stone at time t1 and at time t2. At time t1, t2, of course, we know it's zero because it's reached terminal velocity. And what is it at time t1? At time t1, a stone is dropped. So of course, in the first few seconds, it's going to speed up, accelerate. So the acceleration at t1, wait. Yes, it's t1 is 10. Okay. So when it's dropped, it's going to speed up. So that means it does have some acceleration, right? And that acceleration is equal to the value of g, which is 9.81. We approximated to 10. So at the beginning, the value of g is 10, so the acceleration is 10, and at t2, when it reaches terminal velocity, acceleration is 0. If there's one thing you guys want to remember from this, if none of that made sense, just remember that terminal velocity is constant velocity and acceleration is 0 at that point. That's all. But please don't forget all of the points that I mentioned here, they're equally important. Question number 9. The graph shows how the speed of a car traveling in a straight line changes with time. Which section shows the largest acceleration? Again, I know I've said it 100 times by now, but we're going to do this again. In a velocity time graph or a speed time graph, or any graph actually, the gradient of horizontal line, 0. Slant line, constant. This part, increasing. This is constant, and this decreasing. Now let's look at the sections given here. So, this part, horizontal. Let me color code them. This part is constant, this graph. Horizontal again, constant again, horizontal again, and then negative constant again. It's a straight slant line, okay? So you guys see how this complicated graph is just a combination of these two basic graphs that we've learned, okay? So at what are they asking? Acceleration. We know that the gradient is the acceleration. So at all of these yellow parts, What's your gradient or what's your acceleration? It's just 0. So we're going to cancel those out. But we have A, B, and D. So C is canceled out. Now in A, B, and D, let's look at which one has the largest acceleration. So basically what they're asking us is that which one has the largest gradient? What's gradient? It's the slope of a line. So they're saying which one has the steepest slope. How can you think of slope? Think of slope as just the steepness of a road. Okay? Think that you are in a car and you're trying to climb a mountain. Okay? Or if you're in a car, you're trying to climb a road. You're at this position, you're at this position, and you're at this position. And which of these three would it be the hardest to go up or down? Or which of these three looks the steepest? Of course, A is the steepest. You can see it. It's the steepest. Or another way to figure out which one's the steepest is to see which one's closest to a vertical line. Draw vertical lines at all of these points. I'm going to draw dotted lines. Oopsies. And here. And here. Draw vertical lines and see which of these sections are the closest. So this is the closeness, this is the closeness, and then this is the closeness. And you would see that A is the closest to your vertical line. So answer for 9 is just option A. There you go. Okay, perfect. Let's move on to question number 10. How much battery do I have? 5%. We should be able to get at least 5 questions. An object falls from rest through the air, and the air resistance on it increases. Same case we discussed earlier. Object, we have a stone. It falls through rest. Initial velocity was 0, and its air resistance increases. So here, the weight is going to be the same. Air resistance increases. That means the counter force increases. Object reaches terminal velocity. So at one point, the air resistance is now equal to your weight. So your net force here is 0. Which quantity decreases until its terminal velocity is reached? The net force decreases. Okay, so the net force decreases. And we know that force is proportional to acceleration. So if net force decreases, acceleration decreases. So A is your right option. Do I want to discuss the other parts? Maybe yes. What happens to the weight? It doesn't change. Weight is going to be the constant. Weight is going to be the same throughout. What happens to the speed? The speed increases. It speeds up and then it reaches a constant velocity. The speed doesn't decrease, it increases, and then it reaches a constant value. What happens to the kinetic energy? Kinetic energy also increases because we know that kinetic energy is half mv squared. So 1 over 2 is a constant. A constant just means one number that doesn't change. 1 over 2 doesn't change. Mass is also constant. Velocity is not a constant. It increases throughout the journey. So kinetic energy is proportional to the square of the velocity. If velocity is increasing, that means kinetic energy is also increasing and by a factor of 2. The factor part doesn't really matter, but you should know that they have a direct relationship. Question number 11. An object falls, is it the same question? Nope. An object falls through the air, its velocity increases until it reaches terminal velocity. Which quantity increases? Okay, it's similar, but they're just asking which quantity is increasing now. Acceleration we just saw is decreasing, so that's not the option. Air resistance is increasing. We know that resultant force is proportional to acceleration. It doesn't increase, it decreases. Weight is the same. So let me write some notes here. Weight is the same. This decreases, and this one also decreases. So air resistance is increasing because when something speeds up, when the velocity increases, the resistance that an object faces increases. So air resistance increases. Air resistance is just resistance or friction in air. The speed time graph, battery check, still 5%. The speed time graph represents a short journey. Which distance time graph represents the same journey? Okay. Now, there's two ways to look at it. The first way is to just do it intuitively. An object is speeding up. Okay, so of course it's going to cover more and more distance over time. So the distance will not be the same. So here, in this graph, you see that the distance doesn't change. It's the same value over time. Time's passing by, but the distance doesn't change. So of course this is not the right option. The other three graphs, here, the distance decreases, right? No, it's not decreasing. It is increasing. The distance is increasing. Okay, now all three graphs are reasonable. Let's look at it. So speed is increasing here. We can clearly see that speed is increasing. Speed is increasing. Now, in a distance time graph, why did I do B? Okay, in a distance time graph, the gradient tells you speed. You got it. So the gradient is the speed. Let's look at the gradient of these graphs. A horizontal slant line has a constant gradient. Constant. M means constant speed. Here, an upward-facing curve has an increasing speed, and a downward-facing curve has a decreasing speed. So which is your right option? A, because your speed is increasing. There you go. Question 13. When a heavy coin falls a short distance towards the ground, it does not reach terminal velocity. Why is that? That's your key. So remember that you need some time to reach terminal velocity. You can't reach it in the first few seconds. So the coin has not hit the ground. That doesn't make sense because you don't need to hit the ground to reach terminal velocity. You need to be in the air to reach terminal velocity. So you should not have hit the ground to reach terminal velocity. So that's not the reason why it has not reached terminal velocity. Those were some good number of knots in one sentence, but okay. The weight of the coin equals air resistance. That is not the case. Because when weight of the coin is equal to air resistance, that is when your object has reached terminal velocity. So that is actually the condition for terminal velocity, not the case. Weight of the coin increases as air resistance increases. No, weight is not going to increase. Oh, what am I doing? That's not the option. Weight of the coin is always more than the air resistance, yes. When it's falling a short distance, it hasn't had enough time for it to reach terminal velocity. So throughout its journey, the downward force of the weight was more than the air resistance. Next, a car travels a road at 50 kilometers per hour. The driver applies the same braking force at the same place on a day when the surface is dry, and then on a day when the surface is wet. On the wet surface, how many of these distances are greater than on the dry surface? Now, let's look at all of these things. Braking distance. First of all, what's thinking? Okay, let's look at a journey and then try to understand these terms. You have an object. Okay, you have a car. Okay, these are the red lights or the traffic lights. And the driver is coming here. Okay, at this point, okay, the driver sees the lights turn red. Okay, now of course, when you see the red lights, your brain's going to take a little bit of time to process that information, and then you will apply the brakes. So the car is going to travel a little bit of distance till here maybe, until the driver is able to process the information, and then the brakes are applied. So here, brakes applied. So this distance that the driver covered in processing the information, while he was processing the information, is your thinking distance, so TD, thinking distance, okay? Then the driver applied the brakes, and of course, the car is not going to stop at the very, very instant that the driver applied the brakes. It's going to take a few seconds or milliseconds or whatever to stop. Okay, so the car maybe travels. Oops, oh my god, no. Till here. Okay, so the brakes are applied and the car travels a little bit more distance before it stops. So that is your braking distance. Braking distance. Now, the total distance the car traveled from the time that this driver saw the obstacle or the red light until it stopped is your stopping distance. So the sum of the braking distance and thinking distance is your stopping distance. So this is the sum of the braking distance plus your stopping, oh, sorry, plus your thinking distance. There you go. Okay, perfect. Yeah. Now, think of it technically, okay? If you are driving and it's raining, the surface of the road is now wet. Which of these two things will be affected? Will it affect your uh, thinking capabilities? No, it shouldn't, right? Unless you're too happy. I love rain. Unless you're too happy and distracted by the environment and how pretty everything looks, how clear the sky looks, how pretty the trees look, and you have a lot of dopamine rushing in your brain, and that's making you hyperactive. Unless all of that is happening, it shouldn't affect your thinking distance or thinking time, right? So, a vet road, okay, doesn't affect your thinking capabilities, right? It doesn't affect your reaction time. So thinking distance is not going to be affected. But when you apply the brakes here, there's less friction between the tires and the road, okay? So the less friction there is, the more distance the car is going to cover before it stops. So the braking distance will be affected. If the braking distance is affected, the sum will also be affected. So there's two things that will be affected. There you go. Let's do one last question and then we'll call it a night. The speed time graph for a falling skydiver is shown below. As he falls, the skydiver spreads out his arms and legs and then opens his parachute. Which part of the graph shows the skydiver falling with terminal velocity? What's terminal velocity? Constant velocity. And at what part do you see constant velocity? At A, it's increasing. At B, it's decreasing. Decreasing. Here at D, it's constant. So D is your option. All good? Okay, guys. We did a good amount of questions. I hope it was helpful. I'll try to come back tomorrow and record a few more questions. If you'd like to do any specific topics, please feel free to comment and let me know, and I'll try to cover that section first. Otherwise, I'd like to just continue in a sequence and hopefully complete the sections. What I'm thinking is that I should cover like at least 20 questions from each section first and then come back to every section to record part two because there is about 50 questions in this document and a lot of concepts are repetitive. So I'm not sure if it's a good idea to cover one whole section before I move on to the next, or cover all of them a little bit and then come back to them and record more questions. I'll think about it. For now, all the best, and I'll see you tomorrow. Take care. Bye.